Hello students and welcome to the quick solution of All India Cast Test Series JEE Advanced 2019 Test 1A Paper 1 Code C&D Physics. Let's move to question number 1. In question number 1, speed of particle executing uniform circular motion is 5 meter per second. The magnitude of change in velocity in 0.5 second is 5 meter per second for the first time. Choose the correct options. Then we have to check the validity of these statements. So it is given in the question the magnitude of change in velocity in 0.5 second is 5 meter per second for the first time. So first of all, let's draw a circle. Let this is the circle, and suppose, so initially at t equal to 0, let the particle is at this position. So if I consider this as my x-axis and this my y-axis, I can say the initial velocity of the particle is 5 into j cap, because it is moving in this direction with a speed of 5 meter per second. So let at any time t, when the particle has reached to this position and the position vector makes an angle theta with the x-axis, at that instant if the velocity of the particle is in this direction, then I can write the final velocity at this position will be 5 into, if this angle is theta, then this angle is also theta. So I can say that this velocity can be written as 5 into sine theta minus I cap plus 5 into cos theta into j cap. So it is given in the question the magnitude of change in velocity in 0.5 second is 5 meter per second. So I can say that V final minus V initial, if I take the magnitude of this, so this is equal to 5 meter per second. So if I substitute the value of V final and V initial, then on solving this, I will get theta is equal to pi by 3 radian. So at this angle, the magnitude of change in velocity in 0.5 second is 5 meter per second for the first time. So we know that theta is equal to omega into t. So pi by 3 is equal to omega into t. So for the first time, the value of t is 1 by 2. So by here we can say that omega is equal to 2 pi by 3 radian per second. So this value is in radian. If I calculate the radius of circular path, then I can say that V is equal to omega into r. So r is equal to V, that is 5, divided by omega, that is 2 pi by 3. So it is equal to 15 divided by 2 pi into meter. So at that moment, if I calculate the centripetal acceleration of the particle AC, so that is equal to V square by R. So if I solve this, so it comes out to be, or it is equal to omega square into R. So on substituting the value of omega and R, omega is 2 pi by 3 whole square into R, and the value of R is 15 upon 2 pi. So on solving this, it comes out to be 10 pi by 3 meter per second square. So if I check the options, the angular speed of particle is pi by 3 radian per second. So that is wrong. That is 2 pi by 3 radian per second. So option A is wrong. In option B, the centripetal acceleration of particle is 10 pi by 3 meter per second square. That is correct. The radius of circular path is 15 upon 2 pi meter. So option D is correct. C is wrong. So the correct answer for question number 1 are option B and D. Let's move to question number 2. In question number 2, in the figure, block B of mass M starts from rest from the top of the wedge W of mass capital M. All surfaces in contact are frictionless. W can slide on the ground. B slides down the wedge, moves along ground with a speed V, has an elastic collision with the wall, and climbs back onto W. Then we have to check the validity of these statements. So it is given in the question, all surfaces in contact are considered to be frictionless. So if that is the case, so we can say that when this block of mass M moves downward, then the center of mass of the combined system will move in the vertical direction, and there is no motion of the center of mass in the horizontal direction, as there is no external force acting on the system in the horizontal direction. So we can see that, suppose this is the position at t equal to 0, then at any time t, let this is the position, and at that moment the block reaches to this position. The velocity of the block is given in the question at this moment. It is v and mass is small m. Let at this instant the velocity of this wedge is v0 and the mass of the wedge is capital M. So applying the principle of conservation of linear momentum, we can say that m into v is equal to capital M into v0. Now this wedge moves in the horizontal direction with velocity v0 and this block m moves in this direction with velocity small v. Make an elastic collision with the wall. Till this moment the velocity of the center of mass in x direction is 0. So at the moment when it have a collision with the wall and moves in this direction with a velocity v, at that moment we can say that the velocity of center of mass is m into v plus capital M into v0 divided by small m plus capital M in horizontal direction. So we know that capital M into v0 is equal to small mv. So on substituting this, we can say that velocity of center of mass is 2mv divided by small m plus capital M. Let's check the options. In option A, it is given that B will reach the top of W again. So it means it want to say the block B will reach to the same position. This is not possible because the loss in potential energy of the block M is distributed in the kinetic energy of the block M and the wedge capital M. So it is not possible for the block M to reach the top of the wedge. So option A is wrong. Let's check option B. From the beginning till collision with the wall, the center of mass of the system does not move horizontally. So option B is correct. In option C, after the collision, the center of mass of system, that is B plus W, moves with velocity 2mv upon small m plus capital M. So this velocity I have already calculated. So option C is also correct. Let's check the validity of option D. In option D, it is given that when B reaches its highest position on W again. So it is already given in the question. It is not talking about the top position. So it is talking about highest position of block B on the wedge W. The speed of W is this much. Let's check this. If I analyze the situation when it make a collision with the wall and come back, at this moment we can see that the mass of block is less, so its velocity is higher. So it is moving with higher velocity as compared to this wedge. So it will climb back onto the wedge. So let at any time t dash, at this moment this has moved to this position, and at that moment let the block has come to this position. So at this moment, if it reaches to its highest position, then the velocity of the block and the wedge are same. If I say this is V final, then the velocity of the wedge will increase from V0 to Vf, and at this moment we can say that the velocity of the block M, the velocity of the wedge capital M, and the velocity of the center of mass are same. So at this moment we can say that Vf must be equal to the velocity of center of mass, and this velocity of center of mass in the horizontal direction we have already calculated. So it is equal to 2mv divided by small m plus capital M. So option D is also correct. So the correct answer for question number 2 are option B, C and D. Let's move to question number 3. In question number 3, the ends A and B of rod of length L have velocities of magnitude V and 2V respectively. If inclination of VA relative to rod is alpha and inclination of VB relative to rod is beta, then, so this point is given in the question, that is B. So if I take the component of the velocity along the length of the rod, then we can equate them due to the constraint of the length of the rod. So I can say that VA, that is V into cos alpha, is equal to VB, that is 2V into cos beta. So from here I can calculate the value of beta. So that is equal to cos inverse of cos alpha by 2. So option A is correct and B is wrong. In order to calculate the angular velocity of the rod, we have to take what is the perpendicular component of these velocities to the rod. So I can write omega is equal to, that is V sin alpha, minus of minus VB sine beta. So that is plus 2V into sine beta. So sine beta I can write in terms of 1 minus cos square beta divided by separation between the two ends, that is L. So if I substitute the value of cos square beta, so that is equal to V by L if I take common. So this is equal to sine alpha plus 2 times under root 1 minus cos square beta. So we have already calculated the value of cos beta. So it is equal to cos square alpha divided by 4. So on further rearranging, I can write V by L into sine alpha plus 2 times under root 4 minus 1 minus sine square alpha. So on solving this, we will get the angular velocity of the rod is equal to V into sine alpha. So on further solving, we will see that option D is correct. So the correct answer for question number 3 are option A and D. Let's move to question number 4. In question number 4, a uniform solid sphere of radius r and density rho is attached to one end of the massless spring of force constant K. The other end of the spring is connected to another uniform solid sphere of radius r and density 3 rho. So one sphere has density rho and the other sphere has density 3 rho. The complete arrangement is placed in a liquid of density 2 rho and is allowed to reach equilibrium. Then we have to check the validity of these statements. So first of all, if I analyze the situation, when both the sphere is allowed to reach the equilibrium in the liquid and the density of the one of the sphere is more as compared to other, then physically I can say that this is a sphere of density 3 rho. This is the another sphere of density rho. The radius of both the sphere is same, that is r, and they are in a liquid of density 2 rho. Suppose if I assume let both the sphere are completely submerged in the liquid. So at that instant, if both are connected by a spring of spring constant K, then if I see what is the net gravitational force acting on both these spheres, if I consider this as my system, so the gravitational force acting on a sphere of density rho is 4 by 3 pi r cube into rho into g, plus the gravitational force acting on a sphere of density 3 rho is 4 by 3 pi r cube into 3 rho into g. So if I calculate this, and this is equal to the net buoyancy force acting on this system, so that is equal to 2 times 4 by 3 pi r cube into 2 rho into g. So we can see that the left hand side is equal to the right hand side. See, both the sides are equal. Then from this I can conclude both these spheres are submerged in the liquid. Now the next question is, what is the elongation of the spring? So if I consider this sphere, then suppose the spring force is acting on this in this direction, the gravitational force is acting in this direction, and the buoyancy B is acting in this direction. And if the sphere is in equilibrium, then I can say that spring force, that is K into delta x, let delta x is the extension in the spring, plus the gravitational force. So the gravitational force is 4 by 3 pi r cube into rho into g, that is equal to buoyancy force. So 4 by 3 pi r cube into 2 rho into g. So from here the value of delta x comes out to be 4 by 3 pi r cube into rho into g divided by k. So option A is correct and option D is also correct. So the correct answer for question number 4 are options A and D. Let's move to question number 5. In question number 5, in the given figure, a block of mass m is attached with a system of 3 ideal springs A, B and C. The block is displaced by a small distance x from its equilibrium position vertically downwards and released from rest. T is the time period of a small vertical oscillation of the block. Then choose the correct options, and it is given in the question, pulleys and strings are considered to be ideal. Suppose when the block is displaced by a distance x from the equilibrium position, at that moment the further extension in the spring A is let x1, in spring B let x2, and in spring C let x3. Then I can say that if x1 is the extension in this spring, then the center of the pulley will move downward by a distance x1 by 2. So then if extension in the spring is x2, then the center of the pulley will move downward by a distance x1 by 2 plus x2 into 2 times, because the string get released from these two sides. So 2 times x1 by 2 plus x2. If x3 is the extension, then I can say that if this is displaced by a distance x, then x is equal to x3 plus 2 times x1 by 2 plus x2. So on further solving, it can be written as x1 plus 2x2 plus x3. Now I have to substitute the value of x1, x2 and x3. So initially when the block is in equilibrium, then at that moment I can say that the extension in this spring is y1, the extension in this spring is y2, and the extension in this spring is y3. So at that situation I can say that if I balance the force mg, then I can say that mg is equal to k3 into y3. So my k3 is 2k, that is equal to k2 into y2. So k2 is again 2k divided by 2, and this is equal to k1 into y1. So when the block is displaced by distance x, in the same proportion the x1, x2 and x3 comes. So I can say that if I write the equivalent, so equivalent is equal to mg upon k equivalent is equal to x1. So x1 can be written as mg by k1, and the value of k1 is k, plus 2 times x2. So x2 will be 2 mg by k2. So the value of k2 is 2k, plus x3, and the x3 comes in the proportion of mg by k3. That is k3 is again 2k. So if I solve this, the value of k equivalent comes out to be 2k by 7. So if the value of k equivalent is 2k by 7, then we know that t is equal to 2 pi under root m upon k equivalent. So k equivalent is 2k by 7. So it comes out to be 7 upon 2m under root. So option A is correct. Let's check the validity of other options. In order to calculate the validity of other options, suppose in option B, elongation of spring A is 2 by 7 times the displacement of the block. So if I see the further elongation in A, that is XA or X1, so this is equal to mg by k. So in terms of x, I can say that, so if I solve the value of x in terms of mg and k, then it comes out to be 7 by 2 mg by k. So I can see that this can be written as 2 by 7 of x. So option B is also correct. Let's check option C. Elongation of spring C is 1 by 7 times the displacement of the block. So elongation in spring C is x3. So x3 is equal to mg by 2k. So this is equal to 1 by 2 of 2 by 7 of x. So it is equal to 1 by 7 of x. So option C is also correct. Let's check option D. Elongation of spring B. So in order to calculate elongation in spring B, that is x2. So x2 comes out to be 2 mg divided by k2, that is 2k. So it is equal to mg by k. So I can say that it is equal to 2 by 7 of x. And it is given 4 by 7 of x. So option D is wrong. So the correct answer for question number 5 are option A, B and C. Let's move to question number 6. In question number 6, In the above structure, following parameters are given. Mass of the uniform disc is 15 kg and its radius is 1 meter with center at point B. So this is the disc. Mass of block M is 10 kg. Mass of uniform rod AB is 5 kg and its length is 10 meter. Mass of projected rod PQ is equal to 0, that is weightless. Point A and B are ideal pin support system and C has a rolling base. Based on given information, choose the correct options. So first of all, let's analyze the situation. If the mass of this block is 10 kg, then the weight acting on this is 100 Newton. So the tension T will act 100 Newton. So I can say that if this is my disc, then at this point 100 Newton is acting and at this point 100 Newton is acting. That is tension. The mass of the disc is 15 kg. So the weight acting is 150 Newton. So if I check the validity of these statements, let's check statement A. Supporting force that the pin B would transmit on the disc is this much. And if I see the point B on the disc, then the force acting on the disc in this direction is 250 and in this direction is 100. So the pin will exert the force on the disc in this direction and this force balances these forces. So I can say that if B is the force exerted on the disc by the pin, then the value of FB is equal to 100 into I cap plus 250 into J cap Newton. So I can say that option A is correct. Let's check the validity of option B, C and D. So the supporting force that the pin C would transmit on rod. So now I have to analyze for the rod. So in case of rod, so if I draw the free body diagram on the rod, then on rod 250 is acting in this direction, 100 is acting in this direction. Let the normal force exerted on the rod at C is N. The weight of the rod is acting at this point. The mass is 5 kg, so it is 50. The tension at this point is 100. And let the force at this point AY act in this direction and AX is acting this direction. Since the rod is in the state of equilibrium, so if I write the torque equation about point A, then I can say that torque about point A must be equal to 0 and that is equal to 250 into 10 plus 50 into 5 plus 100 into 1, that is the clockwise torque of this force about point A, minus N into 7. So if I solve for the value of N, the value of N comes out to be 2850 by 7. So I can say that option B is correct because it is given that supporting force that the pin C would transmit on the rod is 2850 by 7 J cap Newton. So option B is also correct. Let's check the validity of option C and D. In option C, the supporting force that the pin A would transmit on the rod. So in order to calculate for A, if I write the equation in X direction for translational equilibrium, then I can say that this 100 force will get cancelled out in X direction. So the value of AX comes out to be 0. And for Y direction, if I check in Y direction, then AY plus 50 plus 250 is equal to N, and that is equal to 2850 by 7. So on solving this, the value of AY comes out to be 750 by 7. So option C is also correct because the supporting force that the pin A would transmit on rod is 750 by 7 minus J cap. So option C is also correct and D is wrong. So the correct answer for question number 6 are option A, B and C. Let's move to question number 7.